Welcome, curious minds, to another deep dive. Today we're embarking on a, well, pretty ambitious journey into a topic that literally shapes every single aspect of our lives.
Mm.
We're talking about the intricate, profound world of building,
Mm-hmm.
from the grandest architectural visions that, inspire awe, to the smallest, most meticulously engineered structural components.
Right.
And of course, the complex human systems that somehow bring them all to life. There's just an entire universe of knowledge waiting for us to explore.
Indeed, there is. And for this deep dive, we've brought together a truly fascinating collection of sources. I mean, everything from ancient architectural treatises that really lay bare these timeless philosophical debates
Yeah.
to modern construction management guides detailing, cutting-edge methods, and even some really insightful philosophical reflections on the very nature of engineering itself.
Wow.
Our mission for you, the listener, is to expertly navigate all this wealth of information. We want to pull out those most important nuggets of knowledge, connect the seemingly disparate dots,
Yeah.
and ultimately reveal the often unseen layers of thought, material science, and human coordination that meticulously shape our physical world.
Think of it as your ultimate shortcut to being truly well-informed about the very foundations of our civilization. Prepare yourself for not just one, but probably a series of aha moments.
Mm-hmm.
And, as always, a few surprising facts about how everything around us is conceived, crafted, and constructed. Let's really unpack this. So, to truly grasp the essence of where we stand in architecture today, we really have to trace our steps back, right back to the beginning, to the ancient masters whose philosophies really laid the groundwork. Our sources, particularly when you look through the lens of figures like Viollet-le-Duc, they illuminate this fascinating and, well, fundamental contrast between two titans of the classical world, the Greeks and the Romans.
Right.
It's a dichotomy that, still resonates.
It really does. And what's truly fascinating here, as Viollet-le-Duc meticulously describes it, are there foundational differences in approach? The Greeks, for instance, they're presented as operating on this profound principle of pure reason, almost like a philosophical pursuit of architectural truth.
Pure reason. Okay.
Yeah, their designs, rather than being just dictated by, say, tradition, they admitted only the vertical point of support, gracefully weighted by these monolithic lintels. Every element was driven by an internal logical necessity.
Oh.
Think about their circular column torus, that base part.
Mm-hmm.
It rested directly on the ground, deliberately avoiding the square plinths that could potentially obstruct passage. I mean, that's a deeply reasoned and, human-centric approach to how people would physically interact with their sacred spaces.
Right, thinking about movement.
Exactly. And their column profiles, often defined by these delicate curves, they were frequently geometrically indescribable.
Indescribable. Like you couldn't just draw it with a compass.
Pretty much. And this wasn't seen as a flaw. It reflected a profound artistic sensibility, a pursuit of organic perfection that went beyond rigid, easily formalized calculations. They even meticulously lessened the space between columns, the intercolumniations, at the angles of their temples.
I'll do that.
Well, not for just arbitrary aesthetic whims, but to ensure both structural stability and perfect visual harmony when you viewed it from different perspectives. It was all adhering strictly to this deep-seated rational understanding of their craft, creating an ideal, timeless form.
Okay, so that's the Greeks' reason, harmony, this kind of indescribable perfection. And then you have the Romans, who were, undeniably master organizers, right? Visionary governors, empire builders.
Absolutely.
But maybe when it came to artistic innovation, they approached architecture with a perhaps different set of priorities compared to the Greeks.
That's a good way to put it. They were pragmatists.
Okay.
They looked at what worked, what conveyed grandeur and power, and they adapted what they saw to their own, massive scale and diverse practical needs.
So they borrowed forms.
Precisely. The Romans adopted Greek forms, like the Corinthian order, but their vision was often one of just monumental scale. They significantly increased the dimensions of these borrowed elements, leading to larger monolithic column shafts.
Bigger is better.
Kind of, yeah.
Yeah.
And the sheer size of these required, just by necessity, the use of square plinths at the base to adequately support these enormous blocks, as Viollet-le-Duc calls them. Their emphasis shifted towards absolute symmetry as a governing law.
Absolute symmetry.
Yeah, and sometimes, as Viollet-le-Duc suggests, even at the expense of pure artistic feeling or the inherent structural logic, he points to examples like leaving a hollow beneath a corner in the Doric frieze purely for the sake of a symmetrical arrangement, even if it kind of defied the structural rationale.
Huh. So form over function sometimes, for symmetry's sake.
You could argue that. Their architects, it's argued, were perhaps not leisure to study purity of line. Instead, stone dressers found it, less trouble to describe a quarter of a circle with the compass than to find an indescribable curve.
The practicalities kick in.
Exactly. This isn't necessarily a criticism, but more an insight into a different set of priorities. Efficiency, grandeur, and an almost administrative, systematized approach to building on an imperial scale. It wasn't that nuanced artistic perfection the Greeks were after.
So what does this historical contrast truly tell us about architecture today? It sounds like this timeless, fundamental debate between the pursuit of pure, almost like you said, ineffable art and the demands of practical application and grand scale. Are we always caught between that perfect, geometrically indescribable curve and the efficient, measurable quarter circle?
Absolutely. And this isn't just some ancient historical footnote. It's a foundational philosophical question that continues to shape our built environment. We see this tension mirrored in more recent history through the critical observations of figures like Rainer Banham.
The 20th century critic.
That's him, a prominent architectural historian. And Banham offers a strikingly similar dichotomy when examining later periods. He contrasts Christopher Wren,
St. Paul's Cathedral.
right, whom he acknowledges as a master builder of talent bordering on genius. Wren, in Banham's assessment, was someone who learned architecture out of books and, excelled at magnificent urban scenography, creating iconic facades like the west front of St. Paul's. Yet Banham suggests Wren perhaps never fully entered the inner sancta of its art or mystery. Meaning he mastered the outward display, the rational application of principles, but perhaps not the deeper, intuitive, artistic essence. Now, compare that with Mies van der Rohe.
The modernist. Less is more.
Exactly. Whom Banham recognizes as a true insider of the arcana of architecture. Mies, according to Banham, genuinely grasped the profound, almost spiritual depths of the art. Yet, here's the paradox. Mies's own profound achievement was ironically obscured by the rhetoric of pure rationality from his followers and interpreters.
How so?
Their explanations of his meticulously crafted minimalist buildings had almost nothing to say about his architecture itself. They focus instead on the logical, the functional, the easily categorized.
So they miss the art.
Banham seems to suggest that. And it raises this incredibly important question for us today. Can we truly explain the essence of great architecture through purely rational, quantifiable terms? Or is there an ineffable quality, a deeply intuitive artistic insight that resides beyond mere logic and into the realm of true art and feeling? A quality perhaps understood by the Greeks and by Mies, but sometimes lost by those who nearly rationalized their work. It's a constant, vital tension.
As we move into the modern era then, we see architects making this conscious, almost defiant break from historical precedents, deliberately forging new paths, trying to define a truly contemporary aesthetic. Figures like Frank Lloyd Wright and Le Corbusier really embody that spirit of innovation and, well, profound redefinition.
They certainly do, each in their own distinct revolutionary way. Frank Lloyd Wright's vision, as it's so richly detailed in his autobiography, was profoundly influential, especially in American residential architecture.
The Prairie School.
Exactly. He was the driving force behind it, with its radical focus on open floor plans, organic architecture, and the use of natural materials. This wasn't just aesthetics, it was a revolution in how people lived in and experienced their homes, aiming to integrate the structure seamlessly with its environment.
Right, connecting inside and outside.
Precisely. His extensive writings reflect his deep philosophical beliefs and insights into the evolving nature of American architecture, culture, and society. He wasn't just a builder, he was a significant cultural commentator, a visionary.
And he stayed in America, right? Didn't go study in Europe.
That's right. Notably, he quite deliberately declined numerous opportunities for studies abroad, choosing instead to retain his own artistic vision influenced by Louis Sullivan rather than conform to European styles.
Wow.
It highlights this powerful, almost fierce struggle for individual identity and artistic integrity, a profound rejection of convention for a personal, deeply held, and uniquely American vision.
And then there's Le Corbusier, a contemporary of Wright, but his approach seems almost the opposite in some ways.
In many ways, yes. Equally groundbreaking, but starkly different. He brought this radical, almost scientific rigor to design, famously declaring the plan is the generator.
The plan is the generator. That sounds very definitive.
It is. For Le Corbusier, a plan was far more than just a preliminary drawing. It was the fundamental essence, the organizing principle, the very raison d'etre of glazing. Without a well-conceived plan, he argued, you are just left with lack of order and willfulness. Chaos, basically.
Okay.
He saw architecture not as mere construction, but as nothing but ordered arrangement, noble prisms seen in light, emphasizing abstraction, clarity, appealing to the highest faculties of the mind. His approach was about distilling form to its purest, most essential, almost platonic elements.
Order and abstraction.
Yes. He passionately aimed for measure or scale, striving to bring life into the whole by means of a unifying and subtle relationship. Every element had to contribute to a harmonious, mathematically ordered composition. He even considered the Parthenon.
Back to the Greeks.
Exactly. He saw the Parthenon as a decisive moment in architecture, offering sure truths and emotion of a superior mathematical order.
Interesting connection there.
It reveals this fascinating continuity of thought, this shared, albeit reinterpreted, pursuit of underlying order. Even his innovative use of prefabricated parts for the Le Corbusier Center on Lake Zurich.
Prefabrication even then.
Oh, yes. It was specifically designed to allow for a completely free ground plan. It shows how even modularity and industrial methods could serve creative freedom and the pursuit of that ideal, abstract plan.
So the plan still reigns supreme.
For him, absolutely. If we connect this to the bigger picture, it's about how fundamental principles of order and expression, whether ancient or modern, continuously seek new forms and technological means to manifest in our built environment.
Okay, so much of architecture starts with these big ideas, these concepts, philosophical principles, but eventually those ideas have to take physical form.
Right.
And that brings us directly to materials and methods, which have changed. Well, not just dramatically over time, but fundamentally redefined what we can even conceive of building.
This is where we shift from abstract thought to tangible reality. And an important question arises. How did humanity even begin to understand and process the very earth beneath our feet to build things?
Good question. Where did we start?
Well, George Agricola's De Re Metallica, published way back in 1556, gives us this incredible, almost cinematic window into early mining and metallurgy.
1556. Wow.
Yeah, imagine he describes intricate mining operations with shafts reaching 60, 80, or 100 fathoms. That's hundreds of feet deep.
That's incredible for that time.
It is. And these weren't just for hauling ore, but crucially for the perpetual, arduous task of extracting water. A constant battle in any subsurface excavation. We learn about stamping machines for crushing ore driven by water wheels and elaborate, carefully designed furnaces for smelting rudest copper ore with a precise mixture of lead slags and schist to separate valuable silver and copper. It's a testament to the immense, painstaking labor and early scientific understanding required.
Trial and error, I imagine.
A lot of it. He even touches upon the historical ambiguity of cadmia, a term then used for various minerals, which eventually turned out to be early forms of zinc, cobalt, and arsenic. It shows the long, iterative, and often imprecise process of material discovery.
So they were figuring out chemistry on the fly.
Essentially, yes. This is where it gets really interesting. The very names of elements and our fundamental understanding of their properties were literally evolving as these early metallurgists experimented, often through trial and error, to harness nature's raw power.
Okay, fast forward centuries from Agricola. We're talking about a much more industrialized, incredibly engineered approach to materials now.
Oh, absolutely.
Our sources detail a whole spectrum.
Yeah.
From the ubiquitous concrete to the immense strength of steel and the renewed sophistication of wood. Each material now has its own complex science, its own specific applications, its own set of challenges.
Exactly. When we talk about concrete, for instance, we're not just talking about one single thing. It's quite varied. We distinguish between plain concrete, which lacks any internal reinforcement,
Right.
cast-in-place concrete, meticulously formed and cured right there on the site.
Okay.
And precast concrete, where elements are manufactured elsewhere under controlled conditions and then brought to the site for assembly.
Like building blocks.
Sort of, yeah.
Yeah.
And even a crucial property like fire resistance, which is paramount for safety, varies significantly. Concrete slabs, for example, can range from, say, 2.5 inches to 7 inches in thickness. And their fire rating depends heavily on the aggregate used, the rocks and sand mixed in. It shows the nuanced understanding required even for this seemingly simple material.
And what about wood? It feels traditional, but you're saying it's sophisticated now.
It really is. We're seeing innovations that go far beyond traditional planks. Consider stressed skin panels. Here, plywood facings are meticulously bonded to lumber stringers, creating a composite material that acts much like an I-beam.
Stronger for its weight?
Exactly. Incredible strength for its weight. And these panels are often engineered to be multifunctional, integrating thermal insulation and vapor retarders. Multiple functions in one component.
Efficient.
Very. But conversely, the sources also remind us that the hands-on craft still exists. Buying rough and green lumber from local sawmills means you'll still be responsible for carefully drying it and precisely surfacing it.
So a mix of high-tech and traditional.
Precisely. It highlights the ongoing variations in material processing.
Okay, and steel. That feels very modern, very engineered.
It is. Steel construction, a marvel of modern engineering, has become incredibly sophisticated. Light gauge steel and open web joists are common for floor and roof systems. They allow for lighter, stronger structures with longer spans. But what's truly fascinating here are the connections, how the pieces join together. Take a welded moment connection, designed specifically to resist the immense dynamic forces of earthquakes.
Okay, earthquake resistance. How does that work?
Well, it might feature this unique dog bone configuration in the beam.
Dog bone?
Yeah, picture the shape of a dog bone. It's an intentional weakening cut into the beam near the connection.
Why weaken it? That sounds counterintuitive.
It does, but think of it like a meticulously designed crumple zone in a car. It's designed so that under immense seismic forces, the beam will deform permanently right there in that specific controlled dog bone zone.
Ah, so it bends there instead of snapping somewhere else.
Exactly. This deliberate deformation absorbs energy and, critically, protects the welded connection against a more severe failure that could lead to catastrophic collapse.
Wow. That's incredible foresight.
Yeah.
Designing for controlled failure.
It's a testament to incredible engineering foresight, yes.
And masonry. Bricks and blocks. Still relevant.
Oh, very much so. But again, not just haphazardly stacking stones anymore. Exterior bearing walls often utilize concrete masonry units, CMUs, frequently paired with steel joists for enhanced stability and robust load-bearing capacity. And even something as seemingly traditional as a fireplace incorporates highly specialized components. You've got fire brick, refractory materials, and fired clay or cast pumice concrete flue liners, all specifically chosen and engineered to withstand extremely high temperatures without degrading or becoming hazardous.
So every single material choice, every connection, it's all a calculated decision.
Absolutely. Based on extensive scientific understanding and decades, if not centuries, of learning from experience and sometimes from failure.
Okay, so once you have the fundamental structure up, the skeleton, the next crucial challenge is making that space truly habitable, comfortable, resilient against the elements. And that involves some serious science, right? Building physics, keeping the outside out.
This leads us to a critical question. How do we ensure both comfort and long-term durability for the people inside and for the structure itself? And it almost always comes down to the careful scientific design of the building enclosure, essentially. The skin of the building.
The skin, okay, like insulation.
Insulation is a prime example of this complex interplay, yes. Our sources discuss both cavity insulation, the stuff between studs, and rigid insulation boards for walls. They specify precise R values, like an R11 or R24 wall. These are quantifiable measures used to calculate a wall assembly's thermal performance.
Higher R value means better insulation.
Generally, yes. Better resistance to heat transfer. Crucial for energy efficiency and indoor comfort. For roofs, insulation can be strategically placed in several positions, but for many insulated roof assemblies, a specific airspace, typically around 1 inch or 25 millimeters, is meticulously required between the insulation and the roof sheathing.
Why the gap?
It's not just dead space. This airspace needs to be connected to the outside with low and high vents. It actively dissipates moisture vapor and prevents damaging heat buildup. Effectively, it allows the roof system to breathe, managing internal moisture and preventing heat stress.
Like ventilation for the roof structure itself.
Exactly. Similarly, a vapor retarder in a crawl space, often just a simple plastic sheet on the ground, significantly reduces the need for underfloor ventilation while effectively preventing damaging moisture intrusion from the soil. Simple detail, but absolutely critical for long-term health and structural integrity.
And what about the openings? Windows, doors? They let light in, but they seem like weak points for weather and energy loss.
They absolutely can be, which is why glazing and openings have seen enormous advancements. Single glazing, just one pane of glass, is now considered largely obsolete, acceptable only in the very mildest climates due to its poor thermal resistance.
Right, you feel the cold right through it.
You do. Most modern building codes now mandate sealed double glazing as a minimum standard. 2 panes with a sealed air gap. And many cutting-edge windows feature triple glazing with a low emissivity low coat.
Low coating. What's that?
It's a microscopically thin, transparent metallic layer, or sometimes they use thin plastic film suspended within the air spaces. These dramatically improve thermal performance by reflecting heat back into the building in winter or preventing it from entering in summer.
Clever.
Very. And the framing around these openings is also crucial structurally. For floors and walls, it's done analogously to wood light frame construction, utilizing doubled members around each opening and strong headers over doors and windows to effectively redistribute and carry the loads that would otherwise be interrupted by these essential openings.
So they're not just holes, they're engineered openings.
Precisely. Carefully engineered, high-performance components within the larger structural system.
Okay, so all these meticulously chosen materials, these precisely defined methods, they have to come together seamlessly. And they do so under the watchful eye of building codes, which you said aren't just arbitrary rules or bureaucratic hurdles. They represent a kind of distilled wisdom.
That's absolutely right. Often wisdom acquired painfully from past failures, all in the continuous pursuit of safety, functionality, and resilience.
So they learn and evolve.
Constantly. Building codes are far from static documents. They are dynamic, living entities. They're continually updated based on new knowledge from design improvements, new materials, and rigorous analyses of actual building performance under extreme conditions, high winds, fires, earthquakes. They dictate everything from the fundamental occupancy classification.
What the building is used for.
Exactly. Distinguishing, for instance, between non-hazardous uses like offices or homes and hazardous occupancies like chemical storage, which then trigger a separate set of special requirements due to their inherent risks.
Makes sense.
And the specifics here are incredibly detailed and impactful. For example, the very mix of different uses within a single building and their relative sizes can significantly alter its classification and the applicable code requirements.
Okay.
For safety, particularly fire safety, automatic sprinkler systems are now broadly required in buildings with 30 or more occupants located 55 feet or more above the lowest level of fire department vehicle access.
So basically most mid-rise buildings need sprinklers.
Essentially, yes. To ensure rapid fire suppression and safe egress for a large number of people, even the seemingly humble door is subject to strict regulation. Egress doors, the ones for emergency exit, must be accessible without pinching or grasping the hardware. That specifically mandates lever handles, which are easier for everyone to use.
Right, not round knobs.
Exactly. And they have to be installed at specific heights, from 34 inches to 48 inches above the finished floor, to accommodate a wide range of users, including those with disabilities. Furthermore, accessible routes are broadly required to connect primary entrances to all accessible dwelling units, though certain steep sites might have carefully defined exceptions for practicality.
So it's about safety, but also accessibility and usability for everyone.
Absolutely. This comprehensive approach highlights how codes reflect not just a continuous learning process in the industry, but also a profound societal commitment to safety, accessibility, and public welfare.
Okay, so building is almost never a solo endeavor. In fact, it's this immense, multifaceted coordination challenge.
Definitely.
Often involving hundreds, maybe thousands of people, countless moving parts, all working towards one goal. And that's where project management steps in. Our sources really underscore the immense complexity of getting a project from just an idea all the way through to successful completion.
Indeed. The PMBOK guide, that's the Project Management Body of Knowledge Guide, is really a cornerstone of modern project management. It outlines 8 project performance domains, key areas that are absolutely essential for successful delivery. It provides a holistic framework for managing complexity.
8 domains. Okay.
And it deeply emphasizes the critical need for constant, ongoing evaluation, checking project progress and direction against the desired outputs, baselines, and business case. It's not just checking boxes, it's about ensuring continuous alignment with the owner's evolving needs and the project's original strategic vision.
Keeping things on track.
Right. And a key concept discussed is tailoring, the art and science of adapting management approaches to individual projects, recognizing that no two endeavors are exactly alike, though often guided by organizational policies for consistency.
So one size doesn't fit all.
Not at all. The guide even delves into servant leadership behaviors, where leaders are actively encouraged to remove obstacles and empower their teams to maximize value delivery. It's a shift from purely hierarchical command and control to enablement and support.
Interesting. So you're saying there isn't just one single way to build or even one definitive, rigid way to manage the whole process? Flexibility seems key.
Absolutely. Flexibility is paramount. The industry has evolved precisely to offer a range of sophisticated approaches because different projects have different needs, different risks, different client relationships. Our sources discuss 4 primary project delivery methods: design, bid, build.
That sounds traditional.
It is. Then design, build, at-risk CM, or CMGC, and integrated project delivery. Each has distinct contractual structures defining the intricate relationships between owners, designers, and contractors, distributing risk and responsibility differently. For a contractor, just deciding whether to bid on a job, the bid-no-bid decision, is incredibly critical. Because of the great deal of time and effort, often thousands of hours, spent preparing detailed estimates with absolutely no guarantee of winning the job, it's a huge upfront investment.
High stakes.
Very. The construction manager, the CM, in many of these models plays a pivotal, proactive role, constantly monitoring designs for scope changes, meticulously evaluating their time and cost impacts, acting as an early warning system.
Trying to catch problems early.
Exactly. They even provide crucial input for contract documents regarding specific safety devices, equipment, and training needed, while explicitly stating the contractor retains primary responsibility for safety. Clear roles. This whole framework feeds into risk management and planning, which is described not as a one-off task, but as a continuous process, integrated from the very start to proactively identify, assess, and mitigate potential problems before they escalate.
Okay, so once a project is officially underway, the focus shifts entirely to meticulous execution. Rigorously managing schedules, controlling costs, ensuring uncompromising quality, keeping everything on track.
Yes, and it's a far more complex challenge than it might seem. Scheduling, for instance, often involves highly detailed precedence diagrams and lag relationships. These illustrate the complex dependencies and permissible overlaps between all the different activities.
It's like a giant flowchart.
Pretty much. Our sources give a specific example from a highway bridge project. An activity like prepare and approve SD footing rebar is allocated a seemingly precise 20 working days. It shows the incredibly granular planning involved.
Breaking it down.
Right. But what's truly insightful here, drawing from Eli Goldratt's The Goal, is the analogy of a hiking line.
Okay.
If one person in the line slows down, the entire line lengthens, creating a cumulative delay. But even if someone speeds up, they can only go as fast as the person immediately in front of them.
Right, you hit a bottleneck.
Exactly. This vividly illustrates how statistical fluctuations, the natural variations in how long tasks take, and dependent events where one task must finish before another starts, create limits on how fast I can go, but no limit on my ability to slow down in a process. This profoundly impacts overall project timelines and shows why you need strategic buffers, not just assume everything will go perfectly.
And costs, of course.
Yeah.
Always a moving target, right?
Yeah.
So many variables.
Indeed. Cost management is a continuous battle against unpredictability. To track this meticulously, they use work package budget control sheets, comparing actual cost versus estimated cost for each work element.
Tracking variance?
Yes. And this data isn't just for the current project. It forms an invaluable database for future projects, refining estimating capabilities. But the factors impacting project cost are numerous and unique to each project. It relies heavily on the art of estimating and an experienced estimator's gut feel to account for unknowns.
Experience matters.
Hugely. Cost fluctuations can arise from revisions in the plans and specifications ordered by the local authority, sometimes unexpectedly, or from unpredictable underground or superstructure conditions, finding unexpected rock or bad soil.
The hidden surprises.
Exactly. And sometimes government agencies might even limit accepted change orders to only project betterments, meaning improvements beyond the original scope, adding layers of financial complexity.
Okay, so beyond time and money, there's the core quality of the build itself, getting it done right.
And the sources explicitly call out quality and safety as contributing so greatly to project success that their control is often categorized as a separate construction management function, underscoring their paramount importance.
So quality isn't an afterthought.
It absolutely cannot be. Quality assurance involves a comprehensive, multi-layered range of checks: field observations, submittals, shop drawings, mock-ups, inspections, and field tests. The fundamental purpose of all these rigorous activities is simply to verify that all materials and workmanship comply with the requirements spelled out in the plans and specifications.
Checking against the blueprint.
Essentially. But this raises an important question. How do you truly ensure consistent quality when construction often happens in complex dynamic conditions, exposed to weather, multiple trades interacting, site-specific challenges, where precise step-by-step rule following is often difficult to prescribe, and on the spot, informed judgment is frequently required?
Yeah, it's not a factory floor.
Exactly. It's a constant challenge of balancing standardization with the unpredictable realities of the job site. Requires deep commitment from everyone.
Okay, this brings us squarely to the cutting edge, where digital tools are fundamentally transforming everything. Building information modeling, or BIM. Huge buzzword. What does it truly mean in practice?
BIM is far more than just fancy 3D modeling. It's a profound paradigm shift in how information is managed and integrated throughout a project's entire lifecycle. It's described as a design and visualization tool, yes, but one that profoundly promises a far better representation of their projects, increase the quality of both design and construction, and increase the speed of construction.
Better, faster, cheaper.
That's the goal. BIM fundamentally makes handling of complex projects with enormous information requirements far easier. This is especially crucial for, say, high-performance green building projects that demand extensive data tracking, recycled material quantities, carbon emissions, indoor air quality performance, stuff like that.
Data management.
Big time.
Yeah.
It can accept plugins that can perform energy modeling and daylighting simulation, allowing integrated performance analysis right in the model. And it serves as a comprehensive platform for managing all the data needed for environmental certifications like LUBI.
So it's not just visualizing the end product. It's about huge improvements in efficiency, collaboration, integrating information across the entire life cycle, from sketch to maintenance.
Exactly. That sounds like a true game changer. It really is. One of the huge tangible benefits is reduced production cycle times. BIM significantly reduces the time required to generate shop drawings and material takeoffs, tasks that traditionally consume vast amounts of labor and are prone to error.
Automating the grunt work.
To a large extent, yes. And this is where it gets really interesting. BIM allows teams to accommodate late changes much more easily and cost-effectively than traditional 2D CAD. Instead of painstakingly updating dozens of separate drawings across different disciplines,
A nightmare.
changes entered into the central BIM model update all affected drawings and schedules almost automatically. Dramatically improves responsiveness, reduces costly errors, enhances project agility.
And clash detection. I've heard about that.
Yes, BIM excels at clash detection, automatically identifying conflicts between different building systems like plumbing pipes, running smack into structural beams early in the design phase.
Before they become incredibly expensive problems on site.
Precisely. It also supports custom parametric objects, allowing designers to create adaptable, intelligent building components that can be easily modified. And in the crucial pre-design phase, the construction manager actively works with the owner to establish the goals and objectives of using BIM, defining its scope, implementation, responsibilities.
Setting it up right from the start.
Exactly. Fundamentally, BIM brings the previously separate functions of planning, design, construction, commissioning, and maintenance management together as an integrated whole. It profoundly optimizes information flow, collaboration, and decision-making among all project participants throughout the building's entire life cycle.
Okay, shifting gears a bit. Buildings don't exist in isolation.
Not at all.
There are threads woven into the rich, complex fabric of our communities and cities. Our sources challenge us to think deeply, almost philosophically, about how these structures interact with and fundamentally shape human life and urban experience.
This leads us to a crucial question. How do we genuinely design cities for people, not just for the efficient movement of automobiles?
A layered debate.
A vital one. Jane Jacobs, the immensely influential urban theorist and activist, famously critiqued planners who prioritized the simple needs of automobile over the vastly more complex needs of cities. She argued passionately for a profound understanding of how the city itself works, with its intricate economic and social concerns, rather than imposing top-down, overly simplistic, often destructive solutions.
The ballet of the sidewalk kind of thinking.
Exactly that kind of observation. Jacobs was a powerful advocate for introducing visual irregularities and interruptions into rigid gridiron plans to generate diversity and liveliness. She argued that vibrant cities thrive on unexpected juxtapositions, complexity, mixed uses.
Not sterile uniformity.
Right. This meant respecting and retaining existing buildings, even creatively incorporating their sides or rears into new frontages wherever possible, creating a desirable mixture of age and textural richness. Her vision was about designing for a dynamic, evolving urban experience that prioritizes human interaction, serendipity, and a sense of belonging over sterile order.
And looking even further forward, beyond just optimizing current cities, we have these visionary movements like the Fab City vision, which sounds, well, almost utopian, rethinking urban production and consumption.
It is ambitious. The Fab City movement, as described in our sources, asks this truly provocative question: what if our cities could be globally connected yet locally productive by 2054?
Locally productive, making things in the city again.
That's the core idea. It's a revolutionary goal to reinvent cities, moving them from being extractive, just consuming resources, to generative, from destructive to restorative, and from alienating to genuinely empowering. The idea is to recover and distribute the knowledge and capacity on how things are made in our cities by connecting citizens with the advanced technologies that are transforming our everyday life, like digital fabrication, 3D printing.
So local resilience, global collaboration.
Precisely. Achieving this grand vision requires cultivating an enabling fab ecosystem. Through a blend of top-down scaling initiatives for infrastructure and research, combined with middle-out and bottom-up propagation to engage a diverse mix of global stakeholders at every level. All participants are encouraged to think like system architects in this distributed, evolving process.
Wow, that's a huge shift in thinking about urban development.
It represents a profound, almost revolutionary shift, yes. Moving towards a truly circular and localized economy, empowering individuals.
Which brings us to another layer, the ethical dimension. As engineers, architects, designers, the decisions we make have profound ethical implications, often balancing competing demands, competing values. What's the right thing to do when, say, public welfare clashes with national security or corporate profit?
Samuel C. Florman touches on this deeply in The Existential Pleasures of Engineering. He asks that fundamental question: how are we to determine what the right thing is? Engineers frequently grapple with this immense challenge, balancing public welfare against, for example, national security demands or corporate profit pressures.
Of choices.
Very. He insightfully points out that different engineers often hold conflicting views on critical issues, things like product harmlessness or even what constitutes frivolous design. The ethical landscape is complex, subjective.
Give me an example.
While one engineer might conscientiously see designing weapons as a necessary contribution to national defense and freedom, another might find it morally abhorrent. A designer might believe people are entitled to have frivolous design purely for joy. Or, conversely, might argue that a totally safe car will encourage reckless driving by removing personal risk perception.
No easy answers.
None at all. Florman highlights that poets and philosophers have been in the forefront of man's rush into the modern world alongside technologists, underscoring the broader human, moral, cultural context of all engineering decisions. It's never purely technical.
Which really circles back to this idea of understanding incredibly complex systems, something Donella Meadows explores so brilliantly in Thinking in Systems.
Yes.
Our actions in one part of a system can have these ripple effects, these counterintuitive consequences we never anticipated.
Her work profoundly emphasizes the constant, vital need to move between structure, diagrams of stocks, flows, and feedback loops, and behavior, time graphs. It's about recognizing that our interventions in complex systems, especially ones as intricate as our built environments, can have significant delayed or entirely counterintuitive effects.
We focus too much on the immediate event.
Often, yes, rather than the underlying structures generating those events. Meadows points out that most of us are surprised by the amount of growth an exponential process can generate. We struggle to intuit how to damp oscillations in a complex system. Furthermore, she stresses that information delivered by a feedback loop can only affect future behavior. You can't deliver a signal fast enough to impact immediate outcomes. There are always delays.
So we need to think long-term, consider the delays, the feedback loops.
Exactly. It reinforces the critical need for thoughtful, long-term design and management in building and urban planning. We must meticulously consider the full spectrum of potential effects, accounting for inherent delays, non-linearities, and often surprising systemic responses. Building a city isn't like assembling a simple machine. It's more like guiding and influencing a living, evolving organism.
Wow. We've truly journeyed through millennia of human ingenuity in building today. From the profound philosophical underpinnings of Greek and Roman architecture to the precise material science of today, the sophisticated orchestration of modern project management, and these visionary concepts shaping future urban environments. It's been a truly fascinating deep dive into the incredible depth and thought behind the structures we often just take for granted.
It really has. Whether you're now admiring the enduring sure truths and mathematical order of the Parthenon, or understanding why that specific welded moment connection with its dog bone shape protects a steel structure during an earthquake,
Right.
or grasping how, for Le Corbusier, the plan is the generator for an entire city, you now have, hopefully, a far deeper appreciation for the myriad layers of expertise, creativity, foresight, and ethical consideration that define our built world. From Agricola's painstaking early metallurgy to the predictive power of BIM, the human drive to shape and refine our environment is this continuous story of innovation, adaptation, and profound reflection.
So here's a provocative thought for you, our listener, to mull over as you go about your day.
Mm-hmm.
In a world increasingly driven by incredibly sophisticated digital models, like BIM, and the localized production promised by these fab ecosystems, if we can now perfectly simulate and predict the structural integrity, the environmental performance, maybe even the social impact of a building before it's even built,
Yep.
what new ethical and aesthetic responsibilities fall upon the architects and engineers who conceive them? And what does it mean for that aha moment of human creativity, that spark of genius in the face of such comprehensive predictive power? Are we building better? Or just more predictably?
A truly compelling question to ponder indeed. Thank you for joining us on this deep dive.
Until next time, keep exploring the hidden depths of the world around you.